This afternoon, I think we have another three talks, I think, right? Yeah. And this talk here will be given by Professor Creemers, who I think, Stefan, you have to correct me if I'm wrong or right, but I think you're a professor of operations research and management science. Is that correct? Is it now at Katholieke Universiteit Leuven or UCL? I'm confused, and I'm a Belgian, so I'm supposed to know, but I don't know. And now I see UCL, and I'm saying it's probably going to be UCL, actually. Is that correct or what? Sorry, Stefan.
As you know, the situation in Belgium, it's always complex. So it was KU Leuven before, and now it has become UC Leuven. So you were partly correct.
Oh, I'm so... I did not know. Okay. So Stefan is associate editor of the Informs Journal of Applied Analytics, and he is definitely a leading researcher in applying quantum algorithms in operations research. So Stefan, the floor is yours. Please go ahead.
Thank you. Thank you, Manuel, for this introduction. Thank you for inviting me. Also, thanks to the Fields Institute for hosting me. Thanks also for Nathan for co-organizing this workshop. I'm very glad and honored to be here. So perhaps first, I also would like to thank Dominic for his presentation. I liked it a lot, and indeed, Emmanuel, as you already said, as an operations researcher, I have solved some real-life optimization problems, and I'm very much aware that in real life, operations researchers have a kind of a fetish to find the optimal solution, but in reality, there are very few companies that really care. And there are even fewer companies that are willing to pay for an optimal solution if there is a good enough solution that can be obtained easily. And in addition as well, many real-life problems, they're rarely nice and well-defined. Often there are some weird constraints, hidden objectives, etc. But in fact, even if you look at nature, even nature does not believe that it is worthwhile to spend resources to find the optimal solution. For instance, if you look at our own brain, it did not evolve to solve problems to optimality. Our brain was evolved to find quick and hopefully good solutions. But okay, that being said, I do think that there is a big role to be played by quantum computing in solving real-life optimization problems, as I will also try to explain in my talk. Now, perhaps to also get back a little bit on this discussion on encryption and the danger of Shor's algorithm, I will also touch upon this in my talk. But as Dominic already mentioned, there is no real reason to be afraid. And also the National Institute of Standards and Technology, or the NIST, has already issued 3 post-quantum encryption standards in 2024. So there is no need for quantum computers to get quantum-safe encryption. Now, that being said, there is a danger of store and decrypt later, where governments and big companies are now obtaining encrypted information, and they will decrypt this later. The question is, of course, what is the value of this information if this can only be decrypted somewhere in the next 10 years? But okay, we'll get back on some of these topics during the presentation. But before I deviate too much, let's get back to optimization, and let's talk about quantum optimization. So, for those of you that are not really familiar with optimization, I will try to give a very brief introduction. And the goal of optimization is, in fact, to maximize or to minimize some sort of objective function given a number of constraints. So, more formally, we could say that we want to maximize Vx, where Vx is an objective function that returns the value of a solution x. And a solution x is a vector that has n decision variables, and xi in x represents the value that can be assigned to a decision variable I. And of course, our solution has to respect a number of problem constraints, and therefore solution X has to be a member of omega, where omega is the set of all feasible solutions. Now, as you can imagine, there are many optimization problems, but in what follows, I will mainly talk about the knapsack problem. And I focus on this knapsack problem because it is a simple to understand problem, and as such, it will allow me to illustrate the dynamics of a number of quantum algorithms. Note that the insights that we're going to discuss in this presentation also hold for other optimization problems. But okay, let's delve a little bit deeper into the knapsack problem. And as you can see, it involves a knapsack. And
Stefan, may I
yes.
interrupt you 2 seconds? I can see that your text is appearing on our screen now. If that's on purpose, that's all great. But basically, we can see it was not on purpose.
No,
Okay,
no,
yeah. Okay, good. Yeah.
I think I can change that.
It's all good. It's all good. Well, now it's not good. It's back again.
And if it's so, it's like this.
No, now we see the text again. We see your text that you're going to say.
Okay, but that's a little bit annoying, of course. Yeah.
It's okay. It's I don't think it's a problem for us, but maybe you're not so keen on.
No, that's okay. I'll try to change it.
Yes, this is very good. I think. Yeah. Could I don't know. Maybe if you go under the right. Oh no,
and like this.
Well, it's no. The text is back again. So we can just see that you very much like to talk of Dominic.
Yeah, indeed.
I just want to make sure that.
And so, okay, very weird actually, but yeah.
But you had Stefan, you had the screen on 5 minutes ago, maybe like 30 seconds ago. You had full screen. Yeah, now it's no. Now the text is underneath now.
Indeed. So this is not going to help.
Yeah.
What I suggest that I will do is that
So I don't know how to use this stuff.
Yeah. I must admit that I tried this beforehand. And,
does anybody know how to make this bigger? How he has to make it bigger? Or Stefan, maybe on presenter view.
Yep.
Do you know?
I can use this.
You were very close to the use presenter view. Yeah, beautiful.
Does this work? Okay.
Yes.
Then we go back.
Okay.
Okay.
So okay, knapsack problem. That's where you. Okay, all good.
So the knapsack problem indeed. Okay, good. Then let's get back. So the knapsack problem is one of the problems that that I'm going to delve into a little bit more in detail because it's a simple problem. And this will allow me to better explain some of the quantum algorithms that I'm going to talk about. Now, so every knapsack, of course, has a maximum weight capacity. And in our example, the maximum weight is 12. That's, of course, because there are 12 slots in this knapsack that are available. So that's corresponding to the maximum weight of this knapsack. Now, we, of course, also have items that we can add to our knapsack. And in our case, we have a candy, we have crackers, we have chewing gum, we have chips, and we have a cheese bar. Okay. Now, each of these items has a certain weight and a value. Okay. Now, the goal is, of course, to decide which items are we going to add to the knapsack. And to do that, we're going to make decisions. And the decision variables that we're going to consider are x1 to x5. And the goal of the knapsack problem is to maximize the value of the knapsack. And we will do that by summing over all of the items. And if an item is added, if an item I is added, that means that xi is 1. And as such, its value will be added and the knapsack value will be updated. Of course, this knapsack problem, we also need to take into account the problem constraints. And for knapsack, there is actually only one constraint, and that is the weight constraint. And that indicates that the weight of the knapsack, of course, should not exceed the weight of the weight capacity of the knapsack. So, if you have a look at the values, or the weights of the different items, we see that the weight corresponds to the space the items take up in the knapsack. And the values, they range from €2 to €8. So sorry that I did not put it to Canadian dollars, but as a European, I'm very proud of the euro, so I'll stick with euros. So the question now is, what is the optimal solution? And perhaps some of you are quick enough to already have figured it out. But the optimal solution adds the candy, the crackers, the gum, and the cheese bar. And this optimal solution, or this optimal knapsack, perhaps it's not really a healthy knapsack, but at least it is the knapsack that maximizes the value, and it has a value of €20. Okay, so as you can imagine, next to knapsack, there are many other optimization problems. So this also implies that there are lots of problem classes. And in this presentation, we're mainly interested in a classification that will consider the computational complexity. And as you can see, there are many complexity classes, but we are mainly interested in 4 complexity classes that we will discuss a little bit more in detail later on. And those are P, NP, NP complete, and NP hard. I know there are also quantum complexity classes and lots of other interesting classes, but we'll not discuss these. To keep things simple, let's focus just on P to NP. For those of you that are not really familiar with complexity theory, I will present again a very brief and probably imprecise introduction into these complexity classes. And in fact, P, NP, NP complete, and NP hard, we can, let's say, distinguish on 2 dimensions. In the first dimension, we can verify, or we can decide whether or not we can verify a solution in polynomial time. So is it possible to calculate the value of a knapsack and the validity of a knapsack, whether or not it's feasible in polynomial time? And yes, we can. The second dimension deals with whether or not we can find an optimal solution in polynomial time. And there, for knapsack, this is not true in general. In general, we cannot find an optimal solution in polynomial time. So, well, perhaps you also wonder, what is polynomial time? I guess that you all know, but to keep it simple, polynomial time means that something is tractable, that we can compute it efficiently, that it doesn't take too much time to compute, that it takes less than exponential time to compute. Now, using these 2 dimensions, we can actually create a diagram. And on this diagram, we have these 2 dimensions, whether or not we can verify in polynomial time, and whether or not we can find an optimal solution in polynomial time. Now, we will try to put these 4 complexity classes onto this diagram. Okay? And the first, perhaps, region or quadrant that is not interesting for us is the quadrant where we have verifiable solutions, or let's say that solutions that cannot be verified in polynomial time, but where we can find the optimal solution somehow in polynomial time. So these classes, or this class of problems, is not relevant for us if there are even problems that exist in this class. Perhaps more interestingly are the problems that belong to class P, because problems in class P, they can be verified in polynomial time, and we can find an optimal solution in polynomial time. And to give an example, the shortest path algorithm that tries to find the shortest path between a location A and a location B, well, that is a polynomial time, let's say, problem, or a problem in P. Next, we have NP. And so for the class NP, all of the problems need to have solutions that can be verified in polynomial time. However, we don't necessarily have to find an optimal solution in polynomial time. In fact, if we're unable to find a solution, the optimal solution in polynomial time, then it means that actually we're in the class of NP-complete problems. Okay, so NP-complete problems, they're very easy to evaluate a solution, but it's very hard to find the optimal solution. Okay? And perhaps you already figured out that knapsack and many other problems falls within this category. They are NP-complete problems. And last but not least, we have NP-hard problems. And for these problems, it in fact does not even have to be tractable to verify a solution. Okay. Unfortunately, many of the interesting problems, they're NP-complete or NP-hard, and they're considered intractable, so they're difficult to solve. Now, some things, this diagram, it's far from perfect, it's very rough, and it also assumes that P does not equal NP. And we're not really certain about this, we cannot prove it, we expect that this is true. But if you have a proof, please contact the guys at the Clay Mathematics Institute, because they will award you $1 million because you have solved then one of the millennium problems. So if you do, please give me a share. Okay, so let's have a look at another graph. And in this graph, you can see how a lot of the NP-complete problems are connected. For instance, you can see that knapsack is connected to the partitioning problem. I can transform the knapsack problem in polynomial time to a partitioning problem. And from the partitioning problem, I can, for instance, go to the bin packing problem, also again in polynomial time. So this means that if I have one NP-complete problem and I can solve it efficiently, I can solve all NP-complete problems efficiently. So it's very important that if you're studying an optimization problem, If you can show that this problem is NP-complete, well, that's a fantastic result. Okay. So, as it turns out, in fact, there are still many problems for which we don't know whether or not they are NP-complete. And here we get to the prime factorization problem. And here we also don't know whether or not this problem is NP-complete or not. Now, why is the prime factorization problem of interest? The prime factorization problem is of interest because it deals with a lot of big primes. So it factorizes numbers in big primes. And this is important because many of the encryption schemes that are used today, that are still used today, they rely on these large primes. And a typical example is RSA, after Rivest, Shamir, and Adelman, who worked at MIT at the time. So they're depicted in this picture. And as you can see, they were also very much interested in this P equals MP question. And probably this has to do with the fact that, in fact, if P equals MP, then we could solve this prime factorization problem in polynomial time. And this would mean that we could break these encryption schemes in polynomial time. So that would be dangerous. Now, the best known classical algorithm that we have factorizes prime only in sub-exponential time. So it's not polynomial at all. If we return to our diagram, we can position the best classical algorithm somewhere over there, where in fact we cannot find a solution in tractable time. Okay, so that's the best classical approach. So all very nice, fantastic, but what does this have to do with quantum computing? And to answer that question, I have to introduce this gentleman who has already appeared in the talk of Dominique. This is, of course, Pete Shor. And Pete Shor, in 1994, he published a quantum algorithm that can factorize primes in polynomial time. And that results in an exponential speedup. Okay, to illustrate, we have the best classical algorithm that cannot be solved in tractable time. And then we have Shor's algorithm that actually only requires polynomial time. So you can see that we have, in fact, an exponential speedup. Okay. Now, the big question is, does this mean that we can get an exponential speedup for solving NP-complete problems? Can we solve NP-complete problems in polynomial time? And unfortunately, the answer to this question is, of course, no. Why? Because it has never been shown in the first place that the prime factorization problem is NP-complete. It may very well be that there is somewhere a classical algorithm that can solve this problem also in polynomial time. In fact, you can imagine that, for instance, if the US government has this algorithm, well, they're probably not going to publish it. Okay, so there are reasons why people would not like to share this algorithm, if it exists. But okay, I don't have it, in any case. So the bottom line here is, if we cannot get an exponential speedup, then the question is, what can we get? What can we get with quantum computing? Well, to answer that question, I'm going to tell you a love story. And perhaps you know Carl. I hope you know Carl from The Simpsons. He's the guy on the left who is holding the bowling shoes. And let's imagine that yesterday, Carl, he went out bowling and he met the girl of his dreams. Okay, and it gets even better because he managed to get her phone number. Now, unfortunately, the day after, Carl was a bit drunk and he has forgotten the name of this girl. So problematic. Luckily, however, Carl has a phone book. But as you know, a phone book, it's not ordered by name. It's ordered by phone number. It's ordered by name, not by phone number, sorry. So this would mean that if Carl would like to retrieve the name of his dream girl, he would have to check all of the entries of the phone book to see whether or not the phone number corresponds to the name. And that way he could figure out the name. Now, as Carl is determined, he starts doing this, but imagine that this phone book has 2 to the power n entries. Well, then that means that in the worst case, Carl will have to check 2 to the power n entries. This might take a while. Only if there was a method that can actually be used to do this fast. And in fact, there is. And to explain how this method works, I will introduce yet another gentleman. And, well, his name is already on the slide, so you can guess it. It's Love Grover. And Love Grover in 1996, he published a quantum algorithm that can find a target entry in an unstructured database that is 2 to the power n entries using only the square root of 2 to the power n lookups. So by looking only at square root 2 to the power n phone numbers. So compared to a classical approach, where we would have to look in the worst case to 2 to the power n phone numbers, this results in a quadratic speedup. Okay, so if we again go to our graph, we have the best classical approach, which requires us to look at most 2 to the power n phone numbers. And then we have Grover's approach, which requires us to look at the square root of 2 to the power n phone numbers. This results in a quadratic speedup. Okay, and it has been shown that, in fact, this speedup is optimal. Grover's algorithm has optimal performance. We cannot do better than this. Okay, so the key takeaway here is that we may probably forget about an exponential speedup, so we cannot achieve what Shor has done, but we can perhaps hope for a quadratic speedup when we are solving NP-complete or NP-hard optimization problems. So this is all very nice, but even with a quadratic speedup, an NP-complete problem remains NP-complete. So in the end, it doesn't help us that much. And also, these results that I've just introduced, they're already more than 30 years old. Okay, the question is, where do we stand now? What is the status quo, the current status quo? And the current status quo is, in fact, that we are in the NISQ era. And the NISQ era, that means that we have at our disposal noisy intermediate scale quantum computers. Okay. In brief, this is again a very rough presentation of reality. There are 2 big approaches for quantum computing. On the one hand, we have quantum computers that rely on the adiabatic principle, and they're also called quantum annealers. Okay? They're machines that serve only one purpose, optimization. And the typical example here is D-Wave. Okay? On the other hand, we also have gate-based computers. And gate-based computers try to achieve universal quantum computing. Here the example is IBM. Here I would like to note as well that once we have this universal quantum computing, well, in fact, it will make, or it may make, classical computers obsolete. Why? Because any classical operation that can be performed on a classical computer, we can also perform on a quantum computer with at most a polynomial overhead. Okay, so one day when we finally have, let's say, universal quantum computing, it may be that classical computers will be obsolete. But we're not there yet. Because our current NISQ era quantum computers, they have a number of limitations, important limitations. First, they have a small number of qubits. And this means that they can only handle problems with a limited size. Second, there is decoherence, which means that we can only maintain the quantum state for a very short amount of time. This means that we have to do all of our calculations in a very short amount of time. So this makes things a little bit more difficult. And last but not least, we have noise, which means that, in fact, when we measure a solution, an outcome, we're not even certain whether or not it's the correct outcome. It may be noise. So very big problems. Now, for the remainder of this presentation, I would like to delve a little bit deeper in these 2 big paradigms of quantum computing. And the first half I would like to talk about adiabatic quantum computing, about quantum annealers. And as you can imagine, quantum annealers also have a number of additional limitations, and I'm going to quickly explain them. First problem is that the original optimization problem, for instance, a knapsack problem, needs to be transformed into a problem that actually can be understood by the quantum annealer. And the typical example there is a QUBO, a quadratic unconstrained binary objective problem. Okay, so that's the first problem. Second problem, a quantum processing unit, a QPU, has a certain topology. And this topology requires embedding. And to show you a number of topologies, we have here the 3 latest QPUs from D-Wave. So we have Chimera, Pegasus, and their latest addition, Zephyr. And as you can see, in these topologies, each qubit is only connected to a number of other qubits. So there is limited connectivity. And that limited connectivity results in embeddings that require chains of qubits. That requires us to chain together different qubits. And these chains, unfortunately, they may break. And if they break, we lose precision. We have noise. Okay. Now, this remains a little bit abstract, so perhaps it's a good idea to look a little bit closer at one of these topologies and to see what this actually means. So let's look at the Chimera topology, and let's again consider the knapsack problem. So imagine that for this knapsack problem, we now focus on only one item. We focus on the first item with decision variable x1, the candy. Imagine that this decision variable corresponds to this qubit in red. Okay, so the red qubit. Now this red qubit, it connects to this green qubit, to this qubit, to this qubit, to this qubit, and to this qubit. So it connects to 5 other qubits. Now imagine that I want this qubit, I want the x1 qubit, to interact with the yellow qubit, which is on the other end of the topology of the graph. So there is no direct connection, so the only option I have is to create a chain. I need to create a chain of qubits. And all of these qubits in this chain correspond to the x1 decision variable. So if x1 is 0, all of these qubits need to be maintained in a 0 state. Of course, the longer this chain, the more likely that it will break up. And if it breaks up, we can no longer guarantee that in all of these qubits, the decision variable is maintained at the same value. Okay, so that's a little bit the problem. I hope that this somehow illustrates the problem here, or the problem with these topologies. To summarize, these topologies have limited connectivity. This limited connectivity makes that we have to embed our problem using chains. So we have to chain together different qubits. These chains may be broken, and if they're broken, we lose accuracy, we lose precision. So that's the problem. Okay, now there are, so quantum annealers have been around already for more than 10 years, perhaps 20 years, and there are many results already. We don't have the time to discuss all of them. So I will try to focus on the results that I know best, and the results that I know best are, of course, the results that I published myself. So what I would like to do next is to discuss a number of papers and to discuss the key findings in these papers. And let's start with the first paper. And this first paper is a collaboration with Luis Fernando Perez Armas. So he was my previous PhD student. He's now a professor in France. And perhaps also important, tomorrow Luis will also present his work during this workshop, and I believe it's at 11:30. So I would let's say, give you, or let's say, recommend that you attend this presentation, because I'm certain that it will be interesting and amusing. So the other, let's say, co-author of this paper is Samuel Delaplanque, also professor in France and a good friend of mine. Now, what did we do in this first paper? Well, we solved the resource constraint project scheduling problem, or RCPSP, which is a typical optimization problem using quantum annealing. Now, what did we do? We used quantum annealing to compare 12 well-known classical formulations to solve the RCPSP. What was the key takeaway? Well, we found out that formulations that work well on a classical computer do not necessarily work well on a quantum computer. In fact, we found out that the oldest formulation, which was not the best formulation on a classical computer, which used the least qubits, in fact, that had the best performance. So it's a bit expected, perhaps, but still interesting. Okay, if we move to a second paper, you see that we have the same authors. The only thing that happened is that the order has changed slightly. And in the second paper, we studied reverse quantum annealing and how we could use reverse quantum annealing to render infeasible solutions feasible. And what did we do? Well, we solved the max independent set problem, MIS, as well as the tree set problem. What was the key takeaway? Well, we found that this reverse quantum annealing may be used to very quickly repair infeasible solutions or to repair solutions that have become infeasible because new constraints have surfaced. So this is particularly useful if we have a setting where we need fast online optimization. And a typical example for this is train scheduling. Imagine that you have a train schedule, a train delays, your entire schedule, well, it's worthless. So you need to repair the schedule very quickly. And for doing that, such a technique, reverse quantum annealing, could be useful. Another example that I included here is portfolio optimization. Well, if you need to react quickly to changes in the stock market, if you want to change your portfolio quickly, again, such a technique may be useful. Okay, if we move to a third paper, there we called in the help of Mr. Riyad Agoun, who is a professor in Luxembourg. And for this paper, we developed a hybrid column generation procedure. So hybrid, it's using a classical computer as well as a quantum computer. So what did we do? We used this procedure to solve the parallel machine scheduling problem as well as the two-dimensional cutting stock problem. What was the key finding? Well, perhaps before I can really explain the key finding, I should explain perhaps that column generation, it decomposes the problem into a master problem and into a subproblem or a set of subproblems. And the subproblem, in fact, generates columns, and columns that can be partial solutions. And these columns are used by the master problem to solve the optimization problem. Now, it is very important for this procedure to be successful, for a column generation procedure to be successful, we need high quality columns. And these columns need to be calculated or need to be obtained efficiently, fast. And in fact, this is what quantum annealers do best. This is where they excel. So what did we do? We used quantum annealing to generate columns in a very fast, efficient way. And these were high quality columns, high quality partial solutions. And we used a classical computer to solve the master problem. And these columns that were generated using this quantum annealer were used as inputs. We found out that this approach actually worked very well. And this confirms that perhaps it's a good direction to take the best of two worlds, to take the benefits of the strengths of a quantum computer and combine them with the strengths of a classical computer. As long as we're in this NISQ era, this might be a viable strategy. Okay. Now, the last paper that I would like to discuss involves a collaboration with Électricité de France, or EDF. So EDF is the producer and the maintainer of electricity in France. They're a very big company, and they're investing heavily in quantum computing because they have very big problems, very big optimization problems, and they cannot solve them that well using classical methods. So they hope that quantum computers will help them to solve these problems faster or more efficiently. And so this is joint work with Saïd Irola, my new PhD, and with Mohamed Hibdi, who is the supervisor at EDF. So what did we do here? We compared different D-wave topologies, so Pegasus and Zephyr, and we used different embeddings to figure out whether or not quantum annealing could be useful. So EDF, in fact, is really looking for a use case, is really trying to evaluate whether or not quantum computing can be useful. And perhaps, as you know, D-wave is the typical quantum annealer that is used. Until a year ago, I think, something like that, an academic license was still free. An academic license nowadays costs 25,000 euros. And if you want to use it commercially, it costs 100,000 euros. So they're doing things that apparently seem to work because companies are paying for that. So that's why we investigated this as well. What are the key takeaways? The first takeaway is that embedding is incredibly important. So if you embed in a good way, well, then your results are much better. Second, in general, this new topology, Zephyr, is much better than the old topology, Pegasus. But this is not always the case. So we see that there is progress. D-Wave is really making their machines better, but it's by small steps. It's not a revolution. Next, we also saw that classical methods, so simulated annealing, that could also be used to solve this problem, and they generally find slightly better solutions. But they're way slower than quantum annealers. So quantum annealing was not 2 or 3 times faster. No, it was 100 times faster. So for ADF, this is sufficient. The use case is made, and they're going to keep investing in quantum computing. They can obtain perhaps not the best solutions, but they can obtain good solutions extremely fast. Okay? And that is often, as Dominic also said, more important in reality than trying to find the optimal solution. Okay? Good. So this, let's say, concludes a little bit what I wanted to say about adiabatic computing. But perhaps there's one more research project that I would like to introduce, and that's an upcoming European research project. The academic partners you already know, it's the usual suspects, but there are also a number of industrial partners that perhaps you don't know yet. So I would like to take the opportunity to introduce them. A first industrial partner is Pascal, and they are in fact a competitor for D-Wave. But the big difference is that Pascal has a neutral atom quantum computer, and this computer would allow for far more flexibility when embedding than a D-Wave computer. So it's a very promising technology, and we expect a lot from, let's say, their quantum computer. The other partner that we have is Kipu, and they're located in Germany. The goal of this project is to benchmark Pascal's neutral atom quantum computer to solve optimization problems. Now, if this project gets accepted, well, we will get several PhDs and several postdocs that will work on this. And I hope that I can come back with you within a few years to present some of the results that come out of this project. I'm, in any case, very curious to see. Okay, so adiabatic quantum computing, what are the lessons learned? First, do not expect that what would work in a classical world, that this also works in the quantum world. Okay? Not at all, actually. And we also know that the current machines that we have, they may not yet be advanced enough to solve the real big problems, but they can already be used as fast heuristics, or they can be used in hybrid procedures to obtain fast but good solutions. So there is a use case already for these quantum annealers. Okay, now let's get next to adiabatic quantum computing. Let's get back to the other paradigm, and let's now talk a little bit more about universal quantum computing. And let's imagine that we have a universal quantum computer at our disposal. First, we perhaps have to note or mention that such a computer does not exist yet, and it may take several more years before we're there. But at this moment in time, we can already simulate one. And that's also what we have done. We have coded our own ideal simulator, and we use that to solve quantum optimization problems. So I know that you can also use existing simulators like Qiskit, but we did not do that because they're far too slow. So we wanted our own simulator in order to be able to do some real computational testing. There are again a number of results that I would like to discuss, 4 papers. And perhaps let's have a look at the first paper, where me and Lewis asked ourselves the question whether or not quantum computing would cause a revolution in the field of discrete optimization. So that's actually a project that we started when Lewis started his PhD. We wanted to figure out, already 6 years ago, whether or not quantum computing would actually be a hype or whether it would be real. So what did we do? We developed several Grover-based quantum procedures for solving discrete optimization problems. And what are the key takeaways? The first takeaway is that we can solve any discrete optimization problem using at most mu times the square root of 2 to the power bn operations. And here, mu is the number of operations we need to verify a solution, and 2 to the power b is the number of discrete values that we can assign to one of the n decision variables. Okay, so that's a bit the first idea. So very versatile, which also means that actually our procedures, they can be used as general purpose solvers. So similar to what Simplex and Groby do for classical computers, these quantum procedures could do for a quantum computer. And next to solving things to optimality, they can also be used as heuristics. Now, one of the procedures that we also developed is a branch and bound procedure. And branch and bound is a very popular, very typical optimization procedure in classical computers, when using classical computers. And when you're using a classical computer, you visit at most 2 to the power n nodes when using a branch and bound procedure. Now we show that if you use a quantum procedure, our hybrid quantum procedure, that you only need to visit the square root of 2 to the power n nodes. So we effectively obtain a quadratic speedup when using branch and bound procedures. We also demonstrate for a given problem, so the knapsack, the binary knapsack problem actually, we demonstrate that we can match the worst case performance of the best classical algorithm. Now this doesn't seem like much of an achievement. We match the worst case performance, but you of course have to be aware that the knapsack problem, it has already been studied for more than 100 years. So the classical algorithms, they're quite advanced, I would say. So if we even can match that worst case performance, we're not doing that bad. And even better, if we look at the quadratic knapsack problem, we are even going to outperform the best classical algorithms. So we can already do that. Now, let's delve a little bit deeper on this quadratic knapsack problem, because it's a rather important problem also for this workshop, which deals with finance. And to explain why, let's perhaps give an example. So imagine that I again have my knapsack. I have here 2 items, crackers and a soda. Adding each item will give me a certain value. But if I go on a trip, perhaps rather than only having some food or a drink, it would also be beneficial. I would like to have, in fact, food and a drink. So bringing both items together also creates value. And in this case, bringing the 2 items gives me an additional value of 4. Now the question is, of course, how do I model this? How do I put this in a model? Well, to do that, I can use what is called a quadratic objective function, where I multiply 2 decision variables, in this case, xi and xj. So, as you probably know, classical computers, they have big problems with these quadratic nonlinear objective functions. They have big problems with nonlinear constraints. They're very difficult to solve. Now, problems that have nonlinear constraints on an objective function, from a quantum perspective, they're not more difficult to solve than problems that have linear objective functions or linear constraints. So this is where quantum computers can really excel, where we expect that in the near future, they will in fact outperform classical computers in these nonlinear quadratic problems. Now, I also told you that this quadratic knapsack problem was important from a financial point of view or from a point of view of finance. And perhaps this is not clear yet, but if you look at the formulation of this quadratic knapsack problem, you might already see something that is familiar. And if you don't worry, yeah? We'll go a little bit more in depth, and let's make the formulation a bit bigger. And let's perhaps also assume that rather than only a weight constraint, I'm going to add an additional constraint which says that the value of my knapsack has to be bigger than a certain value v. Okay, not a difficult constraint, nothing special. Now, rather than my objective function, rather than optimizing the sum of the values, I'm going to optimize the sum of these sigmas, which represent the covariance between items I and j. Now assume that these items are no longer items, but that they are assets. And that this sigma IG is the covariance between the return on asset of asset I and asset G. And then for some of you, this will ring a bell, because this problem is in fact nothing more or nothing less than the Markowitz model. And as you know, this is the foundation of modern portfolio theory, and Markowitz even got the Nobel Prize in economics for this theory. So as I told you, this is indeed an important problem. I did not lie. Okay, let's return to some other results. And there's another paper I would like to discuss, and that's again joint work with Lewis. And here we studied the limitations of a number of existing quantum algorithms that already have been published years ago. And we wanted to verify whether or not we could actually implement this on a quantum computer. And so what did we do? We investigated whether or not quantum counting, nested quantum search, and amplitude amplification could be used for solving discrete optimization problems. And what are the key takeaways? First, if you really want to implement these algorithms, there are several challenges to be overcome. Second, even if you overcome these challenges, we were unable to make sure that, to outperform using these algorithms just a vanilla or textbook implementation of Grover. So a vanilla or textbook implementation of Grover is equally good. So why, in fact, waste our time with complex methods? And also true, these methods, they certainly do not allow to obtain a better than quadratic speedup. As you know, Grover is limited by this quadratic speedup, so these methods are also limited by a quadratic speedup. Okay, so one other paper, which delves a little bit deeper into Grover, since Grover is this important algorithm to which we keep getting back. I was wondering whether or not I could further speed up Grover's algorithm. And I see some of you thinking that but Grover's algorithm is optimal. How can you further speed it up? And you're right, Grover's algorithm is exactly optimal. It has optimal performance, but we can still improve its expected performance. Okay, now how can we do that? Well, we can do this by running Grover's algorithm in series, in parallel, and in series parallel. Now you might ask the question, what is this? Running Grover's algorithm in series? Well, rather than running Grover's algorithm in one long run, after which you are certain to obtain the solution, we could also run Grover's algorithm shorter and do multiple runs in the series. Each run is no longer guaranteed to find the solution, but you have a certain probability. And by doing that, we can reduce the expected number of Grover iterations that we need to find a valid solution. So what are the key takeaways? First, just by running Grover's algorithm in series, we can reduce the runtime by 13%. 13. So that's nice already. Second finding, executing Grover's algorithm in parallel has limited benefit. There's still a benefit, but it's not linear. So it only yields a square root advantage. So for instance, if we use 4 quantum processing units, we will only get a speed up of factor 2, which is sad. And last but not least, all the literature that I've seen that wants to execute Grover's algorithm in parallel says that we have to partition the database. And in fact, I show that this is not true. Partitioning the database is dominated by running Grover's algorithm in series on multiple computers. Okay, so this is perhaps something that is interesting. In any case, if ever in your research or in your applications you want to apply Grover's algorithm, have a look at this paper, in the sense that it will provide you with all the details necessary to determine how to run Grover's algorithm. And on top of that, all of these results, or at least most of them, are closed form results, so they're very easy to apply. Okay, last paper that I would like to discuss is perhaps also the most interesting paper, because I wanted to investigate whether it was possible to design a quantum algorithm that has actually optimal performance when solving discrete optimization problems. First, I have to highlight that I'm not considering the set of all discrete optimization problems. I'm only considering a subset P prime of P, the set of all problems. So these results only hold for the problems in P prime. Note, however, that this P prime, it already contains many well-known problems, such as knapsack, DSP, RCPSP, and some others as well. And it is possible to transform a problem in P into a problem in P prime. So in the end, we can solve this issue. Now, what is the key takeaway? The key takeaway is that for problems in P prime, we are able to obtain a superposition of locally optimal solutions in polynomial time. Okay? So this means that we have a superposition where only the locally optimal solutions have a non-zero probability amplitude. All other solutions have zero probability amplitude. So this is kind of nice if you can obtain that in polynomial time. Now, using this superposition, of course, it becomes rather easy to obtain the globally optimal solution. To further explain these results a bit more nuanced, let's take an example. And in this example, we of course return to our favorite problem, the knapsack problem. And this knapsack problem has 19 items. So this means that there are 2 to the power 19, or roughly speaking, 524,000 possible solutions. And I can put all of these solutions on a graph. And each of these dots represents a solution that has a certain value and a certain weight. Okay? Now, we're going to start from a uniform superposition. This uniform superposition, for this example, would require 19 qubits. If we measure these 19 qubits, we would have an equal probability, a uniform probability to measure any of these solutions. So we have a probability of 1 over 524,000 to measure one of these solutions. Now, that is not really interesting. As you can see, some of these solutions are very good, and some of these solutions may be very bad. The optimal solution, however, will be determined by the weight capacity of the knapsack. And in our example, the weight capacity is 2081. Okay? So this means that all of the solutions on the right of 2081, they're infeasible. They're the blue ones, the blue solutions. All solutions that have a weight less than 2081, they are the feasible solutions, the ones in orange. So now it would be nice to figure out how can we move from this uniform superposition to a superposition where only the feasible solutions are left, where only the feasible solutions have a non-zero probability amplitude. Well, in fact, we're going to do better than this. We're going to obtain a superposition that only contains the boundary solutions, the solutions in green there. Now, what is a boundary solution? A boundary solution is a solution where it's impossible to still add an item without, let's say, violating the weight constraint, without getting a weight higher than 2081. And as you can clearly see, these boundary solutions indeed split the feasible solutions on the left and the infeasible solutions on the right. Okay, they're the boundary solutions. Now, what is cool is that this superposition can be obtained in polynomial time. Now, let's take it one step further. And we can remove from these boundary solutions, solutions that are actually bad. So solutions that have a high weight but a low value. And if we do that, we obtain actually the set of locally optimal solutions. And again, this can be done in polynomial time. Now, until now, I've only discussed, so these are the light blue dots on the graph. Until now, I've only discussed methods that are quite general, and I have not yet taken into account problem-specific information. I can also use problem-specific dominance rules and priority rules to further limit the number of locally optimal solutions to get a better set of good locally optimal solutions. And then you can see that these ones are in purple. In this example, there are 3 of them, 3 locally optimal solutions that are actually good. And again, this superposition can be obtained in polynomial time. And in this example, as explained, there are 3, let's say, locally optimal solutions that are quite good, and 2 optimal solutions. So if I have a superposition of 3 solutions, to get one of the 2 optimal solutions out of it, it's not that difficult. So the groundbreaking thing here is that we can get a superposition of good locally optimal solutions in polynomial time. And to obtain a globally optimal solution, well, what can we do? We can then use a Grover-based search algorithm that can do this. And if we're not interested in the globally optimal solution, but we are already satisfied with a very good solution, well, what can we do? We can just sample this superposition. We obtain the superposition in polynomial time, we sample it. If you want, you can sample it even a few times. It doesn't matter because it's still polynomial time, and you can obtain a good solution. Now, does this imply that we can also find a globally optimal solution in polynomial time? Well, of course not, unfortunately, because there can still be an exponential number of locally optimal solutions. So this means that we still need to search an exponential number of solutions to find a globally optimal solution. So unfortunately, no P is NP. But okay, still, there is something else which is interesting here, because this set of good locally optimal solutions, it may perhaps be seen as a set of unstructured solutions, a set of solutions for which there is no more structure that can still be exploited to obtain the global optimal solution. So if you have an unstructured database, that can be quite interesting. And Lenny, in this case, asks himself the question, why is this important? Well, if I have an unstructured database, we know that Grover's algorithm, in fact, has optimal performance to find one of the valid solutions. So this means that if I find a set of good locally optimal solutions from which all structure has been exploited, so all structure has been removed, and I find this in polynomial time, then I get, in fact, in polynomial time, an unstructured database. And then if I use Grover's algorithm, that has optimal performance, I, in fact, have optimal performance when I'm solving a discrete optimization problem. Okay, so that is impressive. I think this is a nice result. The question is, of course, does this hold for all optimization problems? No, it does not. As explained previously, this only holds for problems in P prime, which is knapsack, TSP, RCPSP, and some other optimization problems. For them, it does not hold. They first need to be transformed. And for instance, you have the 0-1 feasibility problem, tree set, and there are many other problems that cannot be solved in this way directly. But it is interesting to see whether or not we can do this in an efficient way nonetheless. So this is ongoing work, by the way. It's not yet been published, but I think it's clear that these are promising, interesting results. And it's also clear that this opens up several directions for future research. So I guess that I will still be working the coming years on this problem. And I hope that next year or the year after, I can perhaps present some more results. In any case, time to wrap things up. So it's time. So some conclusions. First, as quantum algorithms are inherently probabilistic, it may not be easy to find a linear speedup if we use parallel quantum computing. Second, quantum algorithms can be used as general purpose solvers, as exact procedures, as hybrid procedures, as heuristics. They're extremely versatile. Third, compared to classical computing, we can already obtain a quadratic speedup. And for NP-complete, NP-hard problems, they still remain NP-complete or NP-hard, but from a practical point of view, this quadratic speedup is still very nice. Fourth, quantum computers at this moment, they mainly excel, in general, at solving complex problems that have nonlinear objective functions and/or constraints. So here, there is a real use case on the short run to use quantum computers. And the example here is the quadratic knapsack problem or the Markowitz problem. Once we have universal quantum computing, noiseless universal quantum computing, I'm actually quite certain that this will cause, in the field of optimization at least, a revolution. Okay? And of course, before we're there, we might have to wait a little bit longer or have to be patient a little bit longer because, of course, we don't have a quantum computer yet that is noiseless. We don't have a perfect quantum computer yet. And if you look at classical computers, it has also taken several decades before we had a computer that actually could solve some real big optimization problems. Okay, so this concludes more or less my talk. I hope it was interesting, that you had fun, and I would be happy to answer any questions.
Thank you very much, Stefan.